Welcome to this lesson on pseudo-random number generation in JAX. Today, we'll explore how JAX handles random numbers differently from other libraries like NumPy. This is a crucial topic because understanding these differences is essential for working effectively with JAX. Let's begin with our setup. We'll start by installing JAX using pip. To make our exploration more interesting, we'll use a TPU runtime. Now, let's understand why JAX's approach to random number generation is unique. The key difference lies in JAX's philosophy. It follows what we call a functional programming paradigm. This means JAX avoids using hidden states, which are typically found in classes and traditional random number generators. To better understand this, let's first look at how NumPy handles random numbers. In NumPy, there's a concept called seeding, where an internal state is automatically tracked. NumPy uses a specific type of random number generator called the Mersenne twister. Every time you call a random method in NumPy, you get a different number because the internal state is being tracked and updated automatically within the generator. NumPy allows you to generate both individual random numbers, scalar values, and groups of random numbers, vectors. In contrast, JAX takes a different approach. JAX emphasizes three important qualities: reproducibility, parallelization, and vectorization. To achieve these goals, JAX requires us to manage the random state explicitly. We do this using what's called a key in the JAX random library. A key is a special type of array that corresponds to the specific random number generator being used. In the default setup, each key consists of two unsigned integer values, for example 0 and 42. While this key system might seem similar to NumPy's hidden state, there's a crucial difference. In JAX, we must explicitly manage and pass the key when we want to generate random numbers. This leads to an important characteristic. If we use the same key to generate a random number from a normal distribution multiple times, we'll get the exact same value each time. This is what we call deterministic behavior. The same input always produces the same output. This deterministic nature leads to an important rule. We should never reuse keys. Instead, JAX provides a mechanism called splitting. Splitting allows us to fork the pseudo-random number generator state into new generators. This feature is particularly important for parallel stochastic generation, where we need to generate random numbers across multiple processes simultaneously. Let's walk through how splitting works in practice. When we use the random split function, it gives us two things: a new key and what we call a subkey. An important detail to remember is that once we use the original key for splitting, we shouldn't use it again. We say the key is consumed by the split operation. After getting our subkey, we can use it to generate a normally distributed random value. While it's not strictly required, we can then delete the subkey and use the new key for the next round of generation. This process can be repeated as needed. When we follow this pattern, we'll notice that we get different values from our pseudo-random number generator each time. It's worth emphasizing that even though we're deleting keys to reinforce good practices, the deletion isn't strictly necessary. The important part is avoiding key reuse. Just like the random number generation itself, the split function is deterministic, maintaining JAX's philosophy of avoiding hidden states. Just as we can generate tensors of random numbers in NumPy, we can do the same in JAX. However, there's an important subtlety to understand about how JAX handles random number generation in different contexts. Specifically, if we generate random numbers in a sequential loop, we might get different results compared to generating them in a vectorized way. This distinction is intentional in JAX's design and serves an important purpose. It ensures that we don't interfere with JAX's ability to parallelize and vectorize our code effectively. This is a key feature that supports JAX's emphasis on high-performance computing. This behavior highlights a fundamental principle in JAX. Its design choices consistently prioritize supporting parallelization and vectorization, even in how it handles random number generation. The explicit management of random states through keys and the careful handling of random number generation in different contexts all serve to maintain JAX's core strengths in scientific computing and machine learning applications. These details about JAX's random number generation might seem complex at first, but understanding them is crucial for writing correct and efficient JAX code. The explicit nature of key management, while requiring more attention from the programmer, provides greater control and reproducibility in our calculations. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include a link to the JAX documentation in the description as well. If you have any questions, please post them in the comment section, and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.